And we need to use this term a little bit here, which is a hemiacetal. Let's move this all the way to the top. Let's review some of the chemistry that we saw last week. If we had an aldehyde or a ketone, just use an aldehyde here, and we reacted this with methanol, and let's just use one equivalent to start with. In the presence of acid, you can just put generic H plus or H3O+. We're going to end up forming a species that it's not quite that long, has OCH3 here, and then OH over here. And if we were then to continue this reaction, say with another equivalent, another mole of methanol, compared to 1 mole of that middle species, we would end up substituting both sides. So we'd end up OCH3 here, and then OCH3 here. And we'd end up with water. So the names of these species, we saw that this was our acetal. And this one in the middle, it's halfway to the acetal. And so this is known as a hemiacetal. And let's just for review, I think it's good to, let's consider this mechanism. So nothing new here. And we're only going to go to the hemiacetal. Let's redraw this aldehyde. And we're going to use methanol, and then we'll just stick with this H+, and later on we'll make that H3O+. So the first thing we're going to do is when we have this carbonyl-containing group in the presence of acid is we're going to protonate it. This is going to make this species now much more electrophilic. We could draw a resonance structure for that. But what this is going to do is allow then for our weaker nucleophile, like methanol, to nucleophilically attack, move these electrons up onto this oxygen. So we'll form this intermediate. We'll just draw it similar to what is on the top, like this. And in the last step, we can regenerate our acid by deprotonating. OCH3 plus H3O plus. And this species here, it's going on green, is our hemiacetal. Now we know from our discussion before that we could have this reaction continue. We could go ahead and protonate this hydroxyl group here, make it a good leaving group, and remember, in not SN2, but more of an SN1-like reaction, then this is going to, a lone pair, it will come and reform the carbonyl group, kick out water, it would be, in this particular case, and then we would go on with another attack to form the acetal. But we're going to stop here for right now, because this is going to reflect our initial carbohydrate reaction that we're thinking about. So we have this hemiacetal. And remember, under these acidic conditions, positive formal charge, H+, positive, positive, positive formal charge. Now, let's do the same reaction. Let's put it up far enough so we can see that reaction. But instead of having an external methanol attack, let's consider an intramolecular hemiacetal formation. Let's use an aldehyde. Now let's have this aldehyde be attached here to a hydroxyl group. And now let's see what could happen in the presence of, let's just write H3O+, maybe it's a little more clear, in the presence of acid. So same first step. Under acidic conditions, this aldehyde is protonate the carbonyl group. Making it much more electrophilic. Now, we have to think about what sorts of nucleophiles do we have around? Well, actually, we have one within this same compound, or intramolecular. We have this hydroxyl group here. which could actually act as a nucleophile, and it could attack intramolecularly within the compound to attack the carbon of the carbonyl group. And to just keep track of things here, we have this oxygen, so that's going to end up forming a ring. 1, 2, 3, 4, 5, 6 atoms in our ring. And out of convention, let's put the oxygen in the upper right. We'd end up forming a 6-membered ring. This bond looks like quite on different lengths. Now it's a squiggle. One more time. So that's what it's going to look like. And so now we're forming a bond. This is for this first one here, keep track of things. So this is going to be, the oxygen was number 1. Here it's attacking the carbon. It's going to be number 6. 1, 2, 3, 4, 5, 6. And then let's fill things in. This oxygen has a proton attached to it. Now it has a positive formal charge. And then we have a hydroxyl group that's pointing out here. And then let's just fill it in. It's going to be a little confusing with that 6. Put it in a different spot. Oh no. It's more than I wanted to erase. Sorry. Put the hydrogen here. Let's put the number 6 in again. Squeeze it in there. Now all we have to do is take off our proton. So you can actually redraw this down below. Form the species here. And just to be consistent, I can put the hydrogen in there. So this is really the key reaction in terms of the carbohydrate chemistry that we're dealing with. But what's important to see is that it's the same as the one that's above. We protonate the carbonyl group, so I'm pointing to the reaction above. Here we protonate the carbonyl group. The top reaction, methanol, attacks. Here, forming a new oxygen-carbon bond, generating this intermediate. Here, the bottom one now, oxygen, it's a hydroxyl group that attacks, but rather than methanol, it's within the compound. We form this intermediate, which has a positively charged, positive formal charge, just like here in the top, on the oxygen. And then all we have to do is we deprotonate here in the last step to generate our hemiacetal. And it's the same thing here. We deprotonate to generate our cyclic hemiacetal. So I think it helps to separate the idea of the chemical reaction, the mechanism that we have acetal or hemiacetal formation, and then look at it from an intermolecular, so 2 species, an external nucleophile attacking, versus an internal nucleophile attacking. Same idea, it's just that it looks a little more complicated here. Okay, and we want to make sure that we do not gain or lose the atoms when we're doing this. Now, let's add a little bit more complexity to this. Let's now decorate this species that we have here in the upper, on the left side here, with a bunch of hydroxyl groups. And we're going to do the same thing to have this ring closing reaction. And this is what's going to happen now with a carbohydrate. So I'll just scroll quickly all the way back to the beginning. What we're going to be doing now is going from this Fisher projection here in the middle to this Haworth projection. And what we're going to end up doing is going from those in an aldehyde here to a hemiacetal that we have in the middle.